Hi, welcome to Calculus, section 9.5. Today we're looking at three more convergence tests. We're looking at absolute convergence and then the ratio and root tests. So a series A sub n is said to converge absolutely, or is absolutely convergent, if the sum of the absolute values of the terms is convergent. So that's just a little definition. So here's our absolute convergence test. If the sum from n equals 1 to infinity of the absolute value of the a sub n converges, then the sum n equals 1 to infinity of a sub n converges. So basically, if your series is absolutely convergent, it is also convergent. So a couple of examples here. First one, sum n equals 1 to infinity of negative 1 to the n plus 1, all over 1 over n cubed. So the 1 over n cubed is just going to give us powers of n along the bottom. The negative 1 to the n plus 1 is going to alternate our signs. When n is when n is odd, then we get an even power, we get a positive term, and when n is even, we get an odd power and a negative term. So you can see we just have a series that goes 1 minus an eighth plus 1 over 27 minus 1 over 81. Hold on, that's not right. That third one's not right. That should be 64. Powers of n, not powers of 3. All right. But if we take its absolute value, it's just the sum n equals 1 to infinity of 1 over n cubed. That's just a convergent p-series, right? Our exponent here is greater than 1. So since it's a convergent p-series, the series converges absolutely, which means that the original series converges. Here's a little bit trickier one. We're going to work with cosine. So we have this sum from n equals 1 to infinity of cosine n over n squared. So this is just cosine 1 over 1 plus cosine 2 over 4 plus, going again, powers of n on the bottom, or squares of n on the bottom. But here's the thing. Cosine 1 is less or equal to the absolute value of cosine 1. That is certainly true. And all the way down the line, that would hold. If we take the absolute value of each of these terms, the absolute value terms are bigger. And then since the absolute value of cosine n is less or equal to 1, that's because cosine always spits out values between negative 1 and positive 1. Since that's always less or equal to 1, it converges by comparison to another convergent p-series. We have this beautiful n squared on the bottom. And so since the cosine is guaranteed to be smaller than or equal to 1, we have a series that is smaller than or equal to our convergent series is bigger than or equal to the absolute series is bigger than or equal to the original. And so we get convergence all the way down, and it's wonderful. All right, let's get another board up. All right, let's continue on. So next up, the ratio test. Let the sum a sub n be any series, and suppose that the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to p. So what we're going to do is we're going to compare terms in the series. Then A, the series converges absolutely if p is less than 1, diverges if p is greater than 1, and it is conclusive if p is equal to 1. So I have two examples here. They're pretty fun. I'll show you the first one, and then I have to move the computer down so you can see the second one. Let's look at the sum n equals 0 to infinity of 3 to the n plus 7 all over 4 to the n. All right, so I'm really interested in this absolute value of a sub n plus 1 over a sub n. Please note everything here is positive, so I just threw the absolute value away. So on the top for a sub n plus 1, I just put in n plus 1 for the two n's. So we have 3 to the n plus 1 plus 7 over 4 to the n plus 1, and then on the bottom, we have a sub n, 3 to the n plus 7 over 4 to the n. So I took my fractions and I multiplied by the reciprocal. And when I do that, notice that what happens is 4 to the n and 4 to the n plus 1, they mostly reduce. There's one extra 4 here, so it just leaves 4. Right? 4 to the n and 4 to the n would cancel each other out. 4 to the n plus 1 is just 4 to the n times 4 more. All right, so that reduces. And so I was able to pull a 1/4 out. So I'm now looking at 1/4. I brought the absolute value back for some reason, not quite sure why. But now I have 3 to the n plus 1 plus 7 over 3 to the n plus 7. And then I divided everything by the highest power of n. So I divided by 3 to the n plus 1. No, I didn't. I divided by 3 to the n. That's what I did. Highest in the denominator. So divided by 3 to the n. When I did that, 3 to the n plus 1 over 3 to the n is just 3. Again, an extra 3. 7 over 3 to the n. 3 to the n over itself is 1. And 7 over 3 to the n. I did that so that now I can take that limit as n goes to infinity. Okay, I'm going to evaluate that limit and see what we get. So if we do that, the 7 over 3 to the n and 7 over 3 to the n, those both go to 0. So I just get 3 over 1 times that fourth. So my limit is 3/4, and that makes it convergent by part A. All right, for my second example, moving the computer. All right, you should be able to see it just fine now. Yes, because I'm pointing right at it. The sum n equals 1 to infinity of 2n factorial over n factorial n factorial. So I found it useful here to write out what a sub n and a sub n plus 1 were first. Now, obviously, we already had a sub n, so I probably could have just skipped right to writing out a sub n plus 1. So I put n plus 1 in for all the n's. See that? Be careful. I distributed here and got 2n plus 2, then the factorial, all over n plus 1 factorial, n plus 1 factorial. The nice thing about factorials is it's a lot of multiplication, and so what we're hoping is that a lot of it just drops out of the problem. So if I look at the absolute value of a sub n plus 1 over a sub n, you can see I wrote it out, a sub n plus 1 over a sub n. I got rid of the absolute values because, again, they're not terribly consequential here. Everything is positive. So I took the fraction on the bottom and I multiplied by the reciprocal, and that's where things start to get really fun. So here's what happened for me. Yeah, all right, here's what happens. N and n plus 1 factorial. Let's just look at those first. N factorial is n times n minus 1 times n minus 2 times n minus 3, and so forth. N plus 1 factorial just has one more term, right? It's n plus 1 times n minus 1 times n minus 2 times n minus 3. So what happens is the n factorials drop out, but what's left is still that extra term that each of these has that the n factorials didn't. So we're left with that n plus 1. But notice now we don't have any factorials. That's nice. And for the 2n factorial and the 2n plus 2 factorial, that has two extra terms, right? 2n would be 2n times 2n minus 1 times 2n minus 2, and so forth. This is going to start with 2n plus 2, go down to 2n plus 1, but then we get all the ones that go away. So here I am. I have 2n plus 2 over 2n plus 1 over n plus 1 times n plus 1. Well, I factored a 2 out of that first bit on the top, which allows me to cancel one of the n plus 1s. So I just have 2 times 2n plus 1 over n plus 1, or 4n plus 2 over n plus 1. Again, I evaluated that limit as n went to infinity. I didn't show all the work on this one, but you can divide everything here by n, and you're going to get that the limit is 4. And by part 2 of our ratio test, that means that this is divergent. All right, one more board, hopefully, and then we'll be all done. All right, so our last board is all about the root test. Let the sum of a sub n be any series, and suppose that the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to p. This then converges absolutely if p is less than 1, diverges if p is greater than 1, and is inconclusive if p is equal to 1. So as you can see, I have two examples. Notice I didn't have to do any limits because these just work themselves out beautifully without it. So, first one, the sum n equals 1 to infinity of n cubed over 3 to the n. So the nth root test is super useful here because of that 3 to the n. And so let's see what happens when we take an nth root. When I take the nth root, the first thing I do is I split it top and bottom. So I have the nth root of n cubed over the nth root of 3 to the n. Well, the nth root of 3 to the n, the root and the exponent will just knock each other out. We're left with that 3. On the top, I'm going to rewrite it as the nth root of n cubed, right? We can swap the root and the exponent just fine there. And that's useful because if you remember back earlier in the book, on page 484, one of the limits that we had was that the limit of nth root of n was just 1. So I guess I did do a limit. I did the limit here. So the limit of this gave me 1. So I have 1 cubed over 3, which is just a third. That's less than 1. And so by part A, this converges absolutely. And then last example, sum n equals 1 to infinity of 2 to the n over n to the fourth. This one uses exactly the same set of tricks. I take the nth root of the top and the bottom. I split it. This time I didn't bother with writing out the nth root of 2 to the n. I just wrote it as 2. And then we have the nth root of n to the fourth. Again, I swapped the root and the exponent. And since that limit is 1, we get 2 over 1 to the fourth, or just 2. But 2 is bigger than 1, so that diverges. So there we go. There is our root test. Have a lovely day.